So here is problem number 29 on this series on problem solving and integration calculus. Evaluate the integral of square root of x squared minus 1. This is a very sneaky integral that appears easy but can actually take a while if we don't use the necessary tricks, okay? It might look very, very easy, especially when you see that the inside of the square root there only contains, two terms, and we don't have a fraction, so it appears very, very easy. But it is not that, although it's not difficult, it can be confusing. So let's see how we go about this problem. All right, so to solve this problem, the first thing we need to do is to substitute for this x, all right? Now, when I look at this, I see a Pythagorean identity involving tangent and secant, right? Particularly the fact that secant squared of x minus 1, secant squared of x minus 1 is tan squared of x. So because of that, I'm going to let x be equal to secant of some new variable theta. So let x be secant of theta. If we differentiate that, we get dx by d theta is sec theta tan theta. We've done this again before, so just check it out and see how we managed to do that. This is in fact 1 over cosine of x, or cosine of x into bracket power negative 1. If you differentiate that, you get sine x or sine theta over cos squared of theta, which can be reduced into this, all right? So that's what we do. And now what we need to do is to substitute them like that. So we have, this is our integral here. In place of x squared, we're going to have to put secant squared of x, secant squared of theta. And in place of delta x there, we're going to put theta tan theta d theta. If we do that, so we replace that way based on this substitution, and where there is dx, we will put that like that. All right. Now, secant, the reason I did this in the first place is because I know that stuff inside the square root sign is the same as tangent squared of theta. So therefore, if I find the square root, the whole of that is basically just tangent of theta. All right. And since this is tangent of theta, the whole thing becomes tan squared theta sec theta d theta. All right. So like that, because we know that that inside is tan squared. So if we simplify by Pythagorean identity, that's a Pythagorean identity. So we end up with that. Okay. And now again, we make use of that same Pythagorean identity. We know that tan squared theta is the same as that. So if I replace it back, and so opening that bracket, secant squared theta multiplied by sec theta is secant cubed of theta minus secant of theta. So if we open that bracket, we end up with the integral of sec cubed of theta d theta minus sec of theta d theta. All right. And now we've showed in problem number 28 that the integral, we found the integral of secant cubed of theta, and we also found the integral of sec theta. You can check that out in the clip number 28 and number 23 on topic 5 problems. If you do that, we showed that the integral of secant cubed of theta was in fact a half sec theta tan theta plus half ln sec theta plus tan theta. All right, so that's what we showed earlier. And we also showed in number 23 that the integral of sec theta is in fact ln of sec theta plus tan theta. Okay, so with this information in mind, the integral of, if we take this term and subtract that term, so the integral of secant cubed of theta minus the integral of sec theta, if we do that, then it means we're going to take this expression here and subtract that expression. If we do that, this is positive, and we are going to subtract that. This is 1 here, 1 of this expression. This is half of it. So then we are left with minus half of this expression. Okay, so we'll end up with this term, and then this minus that will give us a half ln of secant theta plus tan theta. So if we do that, we end up with this difference being given by half sec theta tan theta, and it's going to be minus of ln of sec theta tan theta, and that is plus c. So, and this therefore is this integral here, except that our variable is still in terms of theta, so we need to change that from theta to x, but we had let x be secant of theta, so we can basically secant of theta is the same as 1 over cosine. So if x is secant of theta, that means x is 1 over cosine, like that, all right, which is to say that cosine of theta is in fact 1 over x. So if we draw a right angle triangle, and cosine is adjacent over hypotenuse, so adjacent being 1 and hypotenuse being x, we can let that be the theta, the angle theta we are talking about. Then this must be 1 over x to be cosine, and therefore we can find the length of the opposite side to the angle, which is just going to be the square root of x squared minus 1 squared. All right, so x squared minus 1 squared square root, and that means that tangent can now be found, because we need to replace tangent as well. We have replacement for secant, but we don't have a replacement for tangent. Tangent is opposite over adjacent, and so tangent is simply going to be the square root of x squared minus 1. So in conclusion, we are saying that where there is secant, we're going to put x, and where there is tangent, we're going to put the square root of x squared minus 1. If we substitute these into that expression, then we get our integral there to be equal to a half of x because secant is x, times square root of x squared minus 1, and then we're going to subtract ln of x plus square root of x squared minus 1, like that, and then of course plus our constant c, and this is the integral of that expression. So if you're starting this completely from the beginning, then you would need to remember the integrals of secant cubed and the integral of sec of theta. Okay, otherwise if you know that, then it makes life here very easy. All right, so this is the integral of the square root of x squared minus 1 dx. All right, thank you.